Assalamu alaikum, myself Mehak from chemistry department, and today the topic of my presentation is cryonics. So let's get started. These are my outlines: definition of cryonics, history of cryonics, origin of cryonics, what actually happens in cryonics, the physical chemistry, the main damage mechanisms, and why snap freezing is imperfect, ethical, legal, and realistic outlook, the benefits of cryonics, future prospects and research, and the frenzies. Cryonics. Cryonics is the practice of preserving humans or animals at extremely low temperature after legal death, with the hope that future medical technology may be able to revive them and restore them to full health. History of cryonics. Cryopreservation was applied to human cells beginning in 1954 with frozen sperm, which has thawed and used to inseminate 3 women. The freezing of humans was first scientifically proposed by Michigan professor Robert Ettinger in the Prospect of Immortality, 1962. In 1966, the first human body was frozen, though it had been embalmed for 2 months, by being placed in liquid nitrogen and stored at just above freezing. The middle-aged woman from Los Angeles, whose name is unknown, was soon thawed and buried by the relatives. The first body to be cryo-preserved and then frozen in hope of future revival was that of James Bedford. Elker's Mike Darwin says Bedford's body was cryopreserved around 2 hours after his death by cardiorespiratory arrest. On January 12, 1967, Bedford's corpse is the only one frozen before 1974 still preserved today. In 1976, Ettingers founded the Cryonics Institute. His corpse was cryopreserved in 2011. In 1991, Robert Nelson, a former TB repairman with no scientific background who led the Cryonics Society of California, was sued for allowing 9 bodies to thaw and decompose in the 1970s. In his defense, he claimed that the Cryonics Society had run out of money. This lowered the reputation of cryonics in the US. In 2018, a Y Combinator startup called Nectome was recognized for developing a method of preserving brains with chemicals rather than biofreezing. The method is fatal, performed as an euthanasia under general anesthesia, but the hope is that the future technology will allow the brain to be physically scanned into a computer simulation neuron by neuron. Origin of cryonics. The concept of cryonics originated in the mid-20th century from the idea that death might not be a permanent state but rather a process that could be halted or reversed through advanced technology. The term cryonics comes from the Greek word cryos, meaning cold, and refers to the preservation of human bodies at extremely low temperatures with the hope of future revival. The idea was first introduced by Robert Ettinger, an American physics teacher and science fiction enthusiast who is often called the father of cryonics. In 1962, he published a landmark book titled The Prospect of Immortality, which argued that freezing recently deceased people could preserve them until medical science and advance enough to cure their illness and revive them. Ettinger's work inspired many scientists and thinkers, leading to the formation of the first cryonics organizations. In 1967, the first human cryonic preservation took place when Dr. James Bedford, a psychology professor, was cryo-preserved after his death from cancer. Remarkably, his body remains preserved to this day and is often cited as a pioneering case in the history of cryonics. Following this event, several cryonics societies emerged in the United States, such as the Cryonics Institute, CI, founded by the Ettinger in 1976, and Elker Life Extension Foundation, founded in 1972. During the early years, the cryonics faced skepticism from both the scientific community and the public, as the technology required to reverse the freezing process did not exist. Despite criticism, research in cryobiology, the study of the effects of low temperatures on living organisms, began to lend partial support to the theoretical foundations of cryonics, particularly through the development of vitrification techniques, which prevent ice crystal damage in preserved tissues. Today, the cryonics has evolved into a multidisciplinary field combining elements of biology, physics, medicine, and endocrinology. While no one has yet been revived from a cryonically preserved state, the origin of cryonics represents a fascinating intersection between the scientific ambition and the human desire to overcome death. What actually happens in cryonics? Typical sequence. Pronouncement of legal death. A patient must first be declared legally dead with no heartbeat or respiration. Cryonics can only proceed after his declaration. Performing the procedure before legal death would be illegal. It would count as an immediate stabilization field procedures. The goal is to minimize warm ischemic time, the period when tissues lack oxygen at body temperature. A standby term, if available, begins within minutes. CPR and mechanical chest compressions to circulate oxygenated blood, ventilation, oxygenation via airways or ventilator, rapid surface cooling using ice packs or a cooling bath, administration or medications, anticoagulants, buffer solution, metabolic inhibitors to reduce clotting and cellular damage. Transport to cryonic facility. The patient is transported still undergoing CPR and cooling to a cryonics lab or a cooperating mortuary with proper equipment. The goal is to reach the facility within a few hours while maintaining low temperature and perfusion support. Cryoprotective perfusion, vitrification. Once at the lab, the chest cavity is opened and the major blood vessels are cannulated. Blood and water are gradually replaced with the cryoprotectant agents, CPAs, chemicals that prevent ice formation similar to antifreeze. This process is known as vitrification perfusion. Perfusion contains until target CPA concentration is reached, monitored by refractometry or conductivity. Controlled cooling vitrification phase. The patient is cooled slowly under computer control from near 0 degrees Celsius to about 120 degrees Celsius during CPA perfusion. Then further to 196 degrees Celsius liquid nitrogen temperature in stages to prevent cracking or thermal stress. The aim is to avoid ice crystals entirely, producing a glassy vitrified state. Long-term cryogenic storage. The vitrified patient, whole body or just brain, is sealed inside a double-walled tower cooled by the liquid nitrogen. Two storage modes. Immersion storage, fully submerged in liquid nitrogen. Vapor phase storage, suspended in nitrogen vapor to reduce contamination risk. Temperature around 196 degrees Celsius, where all the biochemical activity stops. Indefinite maintenance. The tower requires no electricity, cooling is passive, maintained by periodically refilling nitrogen. Cryonics organizations monitor temperature and nitrogen levels continuously. Preservation is intended to last indefinitely until hypothetical future medical technology can reverse the process. The physical chemistry, freezing versus vitrification. Liquid nitrogen temperature. Liquid nitrogen boils at about 196 degrees Celsius at 1 atmosphere and is the convenient cryogen used in many biological labs because it provides an extremely cold, reproducible thermal bath. At that temperature, the molecular motion for most biological micromolecules are essentially frozen on laboratory timescales. Chemical reaction rates are negligible and diffusion of water and small solutes inside tissues is effectively arrested. Practically, this means that storing biological samples in LN2 greatly shows but does not magically eliminate all thermally driven degradation process, and it provides a temperature far below common glass transition ranges used in cryobiology, giving a large safety margin against slow warming or transient temperature fluctuations. Glass transition safe vitrification region. In cryobiology, the term glass transition refers to the temperature range where an aqueous solution transitions from a viscous liquid into an amorphous solid, a glass. Below the glass transition temperature, molecular mobility is drastically reduced. Diffusion coefficients for water and solute drops many orders of magnitude so that the chemical reactions and rearrangements that would otherwise damage delicate structures are essentially arrested. Cryobiologists commonly treat temperatures around 130 degrees Celsius as a practical threshold. Below this point, many vitrified systems are kinetically stabilized for long-term structural preservation because the timescale for damaging diffusion becomes astronomically long. This is why samples are often cooled into a vitrified state and then transferred into the LN2 for storage. LN2 provides an extra margin below TG in case of slow warming events. Vitrification versus slow freezing, what physically happen? Slow freezing and vitrification are two fundamentally different ways to get an aqueous biological sample to low temperature, and their physical outcomes drive very different types of damage. Slow freezing. As the temperature drops slowly, the pure water freezes into ice crystals because solutes are excluded from the ice lattice. The remaining unfrozen fraction becomes progressively more concentrated. This increases osmotic gradients across membranes and causes cell dehydration. The ice crystals themselves are crystalline solids and can grow into the through extracellular and intracellular species. Mechanically, those crystals shear, puncture, and displace membranes and the delicate extracellular scaffolding, for example, synaptic contacts in neural tissue. Microscopically, this produces membrane rupture, loss of intracellular organization, and mechanical disruption of synapses and cytoskeletal architecture. Thermodynamically, crystal growth releases latent heat, which must be controlled during cooling, and produces especially heterogeneous ice morphology that is different to rivers. Vitrification. Instead of forming ice crystals, the objective is to cool the tissue so rapidly that water solidifies into a amorphous glassy state without long-range crystalline order. A vitrified sample has no ice crystals to mechanically disrupt structures. Solutes are immobilized into the glassy matrix, and osmotic fluxes are arrested when the sample passes staging. Achieving vitrification avoids a mechanical cutting and local solute concentration spikes associated with ice growth. So in principle, it best finds structural features such as synaptic connections and membrane architecture. However, vitrification has its own practical complications. Why vitrification usually requires high CPA concentrations and the trade-offs. Cryoprotective agents CPS such as glycerol, DMSO, ethylene glycol, and propylene glycol change the thermodynamics and kinetics of freezing. They reduce the freezing point, increase solution viscosity, and suppress ice nucleation and growth, all of which favor vitrification at accessible cooling rates. But to reliably vitrify thick tissues to where cooling rates are limited by thermal diffusion, researchers often use high CP concentrations. An experimental example commonly cited is VS55, a vitrification solution whose label indicates roughly 55% total weight by volume of solutes, a mixture of penetrating iron and non-penetrating CPS. Trade-offs and problems with high CP concentration. Number one, toxicity. Many CPS are biologically active and can denature proteins, disrupt membranes, or perturb metabolism in living cells if exposure is prolonged. Toxic effects are concentration and temperature dependent. Some toxicity declines at low temperature but not uniformly. Osmotic stress. Loading and unloading tissues with concentrated CPS create large osmotic gradients that can shrink or swell cells, causing mechanical stresses and membrane injury if not done with carefully controlled protocols. Stepwise equilibration, temperature control. Practical physical hazards beyond ice, thermal stress and devitrification. Even when ice is suppressed, other physical failure modes exist. Differential thermal contraction across heterogeneous tissues can generate mechanical stress and cracking. During warming, if parts of a sample warm faster than others, thermal gradients, stresses and fracture can occur. Also, devitrification, the sudden appearance and growth of ice crystals during warming, is a major cause of loss of structural integrity and function after vitrification. Avoiding it requires controlling warming rates and CP concentration so that the sample travels from the glassy state to temperatures where diffusion allows equilibrium without crossing a region prone to ice nucleation. These are engineering as well as physical problems. Heterogeometry, warming, media, and CPS distribution all matter. Main damage mechanism, and while snap freezing is imperfect, ice formation and mechanical damage. The dominant and most destructive mechanism during uncontrolled cooling is ice crystal formation. When tissue water freezes, pure ice crystals exclude solutes, concentrating salts, proteins, and metabolites in the unfrozen fraction. This has two major effects. Number one, mechanical disruption. Ice crystals grow both inside and between the cells. As they expand, they physically puncture membrane, distort intracellular structures, and sever delicate connections. For example, neural synapses in complex tissues like the brain, where ultrastructure at the nanometer scale encodes connectivity. Even small ice crystals can destroy functional architecture. Dehydration stress. As extracellular ice forms, osmotic pressure increases outside cells, drying water out and causing cell shrinkage. Rapid or even uneven dehydration leads to membrane buckling, detachment, or rupture. This is why slow freezing causes catastrophic injury to biological structure. The slower the cooling, the more time ice has to form and grow. Devitrification during rewarming. Even if the sample is successfully vitrified, no ice on cooling, warming is another critical challenge. As the sample is rewarmed, parts of it may pass through the glass transition range at different rates. If warming is too slow or non-uniform, regions can devitrify, meaning the amorphous solid locally crystallizes as it warms. Devitrified ice formation during warming causes the same mechanical and osmotic damage as freezing, often even more destructively because it happens suddenly and unevenly. Molecular and biochemical degradation, long-term storage. Molecular and biochemical degradation, long-term storage. At typical cryonic storage temperatures, diffusion and reaction rates are negligible. But if storage is imperfect, for example, periodic warming above 130 degrees Celsius, slow degradation processes could occur. Free radical reactions, residual enzymatic activity, chemical decomposition of CPAs or biomolecules. Snap freezing might sound good but fails in practice. Snap freezing means the plunging tissue directly into a cryogen-like liquid nitrogen to cool it extremely rapidly. The intuition is that faster cooling means less time for ice to form, which is true for thin samples, but it fails for bulk tissue because of thermal gradients and heat transfer limits. Thermal stress and fracturing. When large samples like organs or whole brains are cooled to cryonic temperatures, thermal contraction occurs unevenly. Different regions and materials shrink at different rates. Below the glass transition temperature, the materials behaves like a brittle glass. If the cooling or warming is not perfectly uniform, mechanical stress builds up, leading to the cracking or the fracturing. In cryonics, where samples may be many centimeters across, these fractures can propagate to entire brain regions or organs, preserving the geometry but destroying continuity at the microscopic level. Even if vitrification prevents ice, mechanical fracturing remains one of the major unresolved forms of physical damage in large samples. How many people, facilities, and how stored? How many people? The Elker Life Extension Foundation, based in Arizona, USA, reports 248 patients in cryopreservation and 1,442 cryopreservation members, people who have made full legal and financial arrangements as of February 28, 2025. The Cryonics Institute, Michigan, USA, has over 250 patients currently in cryostasis, according to their website. The articles estimate around 500 people worldwide have been cryopreserved to date. The number of people assigned up members is larger, but precise global members are unclear. Major facilities and how it's stored. Elker stored both whole body and neuropreservation, brain only patients. The process. After legal death, cooling begins, blood is placed with cryo protectant, and then the body or brain is cooled to about 196 degrees Celsius liquid nitrogen for long-term storage, standard in the cryonics. These storage patients are often called such, though no revival has occurred. As you can see, Cryonics Institute CA primarily offers whole body cryopreservation. The facility in Michigan houses cryostates, liquid nitrogen tanks. Each cryostat may contain multiple bodies. For example, one source says each unit contains up to 8 people. Their website states over 100 patients in cryostasis at this facility in one passage. This is the Cryonics Institute. How they are stored. Some of the technical details. After legal death, the body is cooled, sometimes started on site to slow decay. Blood fluids are replaced by a cryptoprotectant to reduce ice crystal formation damage. The patient is then cooled slowly to very low temperature, often about 196 Celsius, the boiling point of liquid nitrogen, and placed in a cryostat. They remain in this suspended state until some future date when revival technology might exist. For example, Elker's fact sheet says Willy body cost is $20,000 and neuropreservation $80,000. Safety and practical risks of liquid nitrogen in cryonics. Extreme cold, cryogenic burns, and material brittleness. Hazard. LN2 has a boiling point of 160 Celsius. Contact with skin or ice causes instant frostbite or cryogenic burns. Controls. Use insulated gloves, face shields, and cryogenic crates, aprons. Avoid trapping LN2 in closed system where rapid vaporization can cause pressure buildup or explosions. Material risk. Many materials, rubbers, certain plastics, mild steel became brittle and can crack at cryogenic temperatures. Asphyxiation risk, oxygen displacement hazard. When LN2 vaporizes, it expands 700 times in volume as nitrogen gas, displacing oxygen. In enclosed or poorly ventilated spaces, this can quickly lead to the hypoxia or death. Control. Continuous oxygen sensors, alarms, mechanical ventilation or to prevent gas buildups, personnel training to recognize symptoms of oxygen depletion, dizziness, confusion or loss of consciousness, never enter confined LN2 storage areas without purification or safe oxygen levels, pressure and explosion hazards. Hazard. Sealed containers of Ln2 can explode if warm due to rapid vaporization. Controls. Use pressure relief valves and open vents on all Ln2 containers. Never store Ln2 in thermos-like vessels without venting. Oxygen condensation and fire risk. Hazard. In open systems, atmospheric oxygen can condense into liquid form on cold surfaces, enriching the environment in oxygen and increasing flammability. Controls. Maintain separation from combustible materials, minimize open exposure of Ln2. Cryonics specific practical challenges. Continuous supply dependence. Ln2 balls of steadily loss of supply and maintenance lapses can cause irreversible warming and tissue damage. Storage safety. Cryonics facilities typically use large phase devices to reduce risk of immersion and minimize boil-off losses. Redundancy and monitoring. Automated level monitoring, backup tanks, and alarm systems are essential for long-term storage reliability. Cryonics ethical, legal, and realistic outlook. Realistic outlook. Cryonics aims to preserve the human body or brain at very low temperature after legal death, with the hope that future technologies might restore life and health. However, revival remains purely speculative. Achieving it would require several breakthroughs that do not currently exist. Molecular scale repair of cells and synapses damaged by freezing, dehydration, or chemical toxicity, reconstitution of dead or decayed tissues, including the brain, without loss of structural informational integrity, restoration of the blood circulation and metabolism without destroying delicate preserved structures, reversal of cryoprotectant, CPS toxicity, and fracture damage from the cooling. Cures for the original cause of death as viable alone wouldn't address underlying disease. Ethical outlook. Cryonics raises deep ethical questions. Autonomy and consent. Ethically permissible if individuals choose cryonics with full understanding of its speculative nature, deception and hope. Ethical concern arises if cryonics is marked as a form of life extension rather than an unproven experiment. Transparency about uncertainty is critical. Resource allocation. Critics question whether investing large sums in cryonics is ethical, while resources could help living patients. Supporters could encounter their private funding and future potential justify continued exploration. Identify and personhood. Even if revival were possible, questions remain about whether the revived individual would retain the same consciousness or identity. Post-revival ethics. Hypothetical issues include the legal or moral status of revived individuals, integration into future society, and responsibility for their welfare. Legal outlook. Legally, cryonics exist in a gray area. Declared death. Cryonics can only proceed after legal death is pronounced. The individual is considered deceased, and preservation is treated as a form of body disposition, not medical treatment. Regulation. Few jurisdictions explicitly regulate cryonics in the US. Is largely governed by the state laws on funeral practices and contacts between cryonics organization and clients. Legal personhood. Revived individual, if revival were ever occurred, would face complex legal questions. Are they the same person legally or a new entity? What happens to their prior rights, property, and identity? Consumer protection. Ethical and legal scrutiny focuses on ensuring organizations don't mislead clients about the chances of success. Some critics call for stricter oversight to prevent fraud or exploitation. Short myths. They freeze people in liquid nitrogen and can bring them back later. Myth. Bodies aren't just frozen, they are perfused with cryoprotectant, CPS, and vitrified to reduce ice damage. Even so, toxicity, cracking, and cellular damage will still occur. No revival technology exists. You can thaw a frozen person and they will wake up. Myth. There's no evidence that a whole organ, brain, or body can survive vitrification and rewarming intact. Only small tissues or cells sometimes recover after careful cryopreservation, not complex organisms. Benefit of cryonics. It prevents the possibility of future revival. Cryonics is not about freezing people and waking them up later. It's about preserving biological information, especially in the brain, that might allow future scientists to repair and revive a person. Even though today's technology cannot do this, cryonics offers a non-zero chance of survival compared to burial or cremation, which guarantee destruction. It prevents the brain structure and information. Modern cryonics uses cryoprotectants and vitrification to reduce ice damage. This process helps maintain fine neural structures, potentially including potentially including the physical basis of memories and personality, so that if advanced repair methods are developed, a person's identity might be recoverable. It could enable future extension. If revival ever becomes possible, medical advances might also reverse aging, cure disease, and regenerate damaged tissue. Cryonics could then allow individuals to live in a future with vastly improved health and longevity technologies. It supports scientific progress. Cryonic research overlaps with cryobiology, neuroscience, and organ preservation fields that already benefit medicine today. Techniques developed for cryonics may one day help store organs for longer, preserve cells or tissues more effectively, and improve emergency medicine, for example, suspended animation. It provides philosophical and emotional comfort. Furthermore, cryonics offers peace of mind, the idea that death may not be final and that the one taking a proactive step towards the future. It gives people hope and a sense of continuity even if the odds of success are uncertain. Future prospects and research. Advances in cryobiology and nanotechnology. Cryobiology, the study of biological materials at low temperatures, continues to make significant progress towards solving one of the cryonics' biggest challenges, preventing cellular damage, freezing and thawing. Modern cryonics uses vitrification, a process that replaces bodily fluids with cryoprotectants to prevent ice crystal formation. Recent research focuses on improving cryoprotectant formulas to reduce toxicity while maintaining the tissue integrity. Nanotechnology also holds great promise for cryonics in the future. Nanobots could potentially repair damaged cells, reconstruct tissues, and restore molecular structures altered during preservation. These nanoscale tools may even be able to reverse the biochemical effects of freezing, paving the way for safer revival procedures. Possible revival methods. Scientists have proposed several potential methods for reviving cryonically preserved individuals, though none are currently achievable. Cell repair. Future biotechnology may enable the repair of individual cells and tissue damaged during preservation using advanced nanomedicine or molecular repair mechanisms. Digital mind reconstruction. Some researchers suggest scanning and uploading the brain's neural patterns into a digital medium, effectively recreating the preserved person consciousness. This would rely on advances in neuroscience, brain mapping, and artificial intelligence. Cloning and regeneration. Another proposed approach involves cloning the preserved person's DNA and transferring stored memories or neural data into the cloned body. Although the largest speculative method reflects the intersection of cryonics with the regenerative medicine and synthetic biology. Scientific skepticism and optimism. The future of cryonics inspires both optimism and skepticism. Supporters argue that continuous progress in medicine, AI, and nanotechnology will eventually make revival possible, pointing to past medical milestones like organ transplantation and genetic editing once deemed impossible. However, skeptics highlight the major obstacles: irreversible damage to cells, known effects on brain information storage, and ethical questions about reanimation. The lack of proven revival from full body cryopreservation means cryonics remains a theoretical hope rather than a practical science. Nevertheless, research in related fields keeps its ideas scientifically intriguing. Cryonics in comparison to other longevity technologies. While cryonics aims to preserve life after legal death, other longevity technologies focus on extending life before the death occurs. Artificial intelligence (AI) used in healthcare to predict diseases, optimize treatment, and potentially enhance brain machine interfaces for cognitive longevity. Genetic therapy targets aging at the cellular level by repairing or modifying genes responsible for degeneration. Compared to these, cryonics is the last resort technology dependent on future breakthroughs to restore life. Yes, if successful, it could complement these approaches, offering to a form of time travel through death, bridging current medical limits to future cures. Summary. Typical procedures. Begins after legal death is declared. Immediate stabilization, CPR, oxygenation and cooling to slow decay. Transport to a cryonics lab or facility. Perfusion. Blood replaced with cryoprotectant agent CPS to prevent the ice formation. Controlled vitrification, tissue cooled to form a glass-like solid, no ice. Long-term storage in liquid nitrogen or vapor phase systems. Physical chemistry. Freezing machine vitrification. Liquid nitrogen glass transition region below 100 degrees Celsius, diffusion steps, structure stable. Freezing. Ice crystals damage cells. Vitrification avoids ice but needs high CPA levels. Trade-off: less ice, more CPA, toxicity and osmotic stress. Major damage mechanisms. Ice crystal damage tears membranes and brain circuits. Cryoprotectant toxicity and osmotic stress harm cells if CPA is added to move too fast. Thermal fractures occurs as tissues contract unevenly during cooling or warming. Chemical fixation or versus reversibility. Good structure preservation may prevent biological revival. What research shows? Small sample cells, embryos, thin cells can be vitrified and embalmed successfully. For whole organ or brain, no successful revival yet. Recent studies 2022-2024 showed improved CPA formulas and structural preservation, but scaling to humans remains unsolved. Brain studies show the fine structure preserved in animals, but identity, memory retention is unknown. Current facilities and numbers. Estimated preserved individuals 200 to 500 worldwide. Major facilities Elker, Cryonics Institute, and a few in Russia and Europe. None revived so far. Safety and liquid nitrogen risks. Hazards: extreme cold and oxygen displacement. Safety measures: ventilation, oxygen sensors, and vapor phase storage. Liquid nitrogen is inert but thermally dangerous. Ethical, legal, and realistic outlook. Revival is speculative. Future requires future nanotechnology, cell repair, and curing original causes of death. Scientific consensus: cryonics is unproven and theoretical. Cryobiologists contribute to preservation methods, but revival gap remains vast. References. These are my references: Elker Life Extension Foundation Procedure and Stats. Pahir at Vitrification Chemistry, recent PMC reviews. OSHA reports, Frontiers in Medical Technology 2024, Cryonics Institute, and FAHI GM, Cryopreservation of Complex Systems. Thank you so much. Allah Hafiz.